Welcome to the last lecture of the quarter for CS231N. And it was great to see you guys at the beginning and now at the end. This lecture is a little bit of a departure. We're not going to teach any new materials in terms of algorithms. It's more a talk that I'd like to give to students to put a perspective both on a more longer term research evolution, but as well as another dimension that is important to today's AI, which we would call it the human perspective. So for the completeness of the material, there's a little bit of an overlap that you might see from other parts of this course, but hopefully it makes sense in a fuller way. So the title of this slide or this lecture is What We See and What We Value, AI with a Human Perspective. And I know that some of you have already heard about this, is really the beginning, the origin of vision, both in terms of evolution as well as in terms of our technology. And we did talk about the first light that came to the animal world back 540 million years ago. And that was when animals, or trilobites to be specific, developed photosensitive cells to glean what the outer world is about. And according to zoologists like Andrew Parker, what happened is that because of this the onset of vision, it set off an evolutionary arms race where animals either evolved or died. And that arms race gave rise to the speciation or explosive speciation of animals, which now zoologists call the Cambrian explosion or the Big Bang of evolution. And of course, you wouldn't be surprised that vision is still to this day a primary sensory intelligent system in many, many animals. Not all animals use vision, admittedly, but many do. And that's also one of the primary sensory systems for humans. And we use vision to do everything from survival to work to entertainment to socialization to learning, development, and many other things. So that's the recapture or summary of evolution. And we also briefly talked about computer vision being a summer vision project back in the 1960s as an attempt to use a couple of undergrads to construct the significant portion of the visual system. And that was very in line with the history of AI, where we tend to have clarity of the North Star, but underestimate how long it would take. We are still probably experiencing that today, but a lot has happened, right? Like, you don't need me to tell you that from empowering self-driving car to understanding images to the generative AI revolution we're seeing, vision is playing a huge role and also in many parts leading the wave. So maybe it's time to just take a different look at this, both historically and going towards the future. Is where have we come from and where are we going? And this is an important topic to discuss, because a lot of what has happened will inform what will happen. So I'm organizing this talk in 3 chunks. First of all, building AI to see what humans see. And that's where we came from. That we were so inspired by human capability that we want to make machines that do the same. And then we'll talk about building AI to see what humans don't see. And then we'll finish with building AI to see what humans would like to see. Let's just start with the first one, building AI to see what humans see. Again, just a little bit of a review. Humans are so good at seeing. We know this. This is a very half a century old experiment showing us that even watching a video you've never watched, played at 10 hertz, which means every frame is only about on the screen for 100 milliseconds. You've never seen that. It's still no problem for human eyes to detect a target, in this case, a person, in this complex scene where you have no idea, a prior knowledge about what this person is. It really underscores the superb ability of human visual understanding, especially object-focused understanding. We also have briefly mentioned that around the turn of the century, neurophysiologists are measuring the speed of vision in terms of humans seeing complex objects in the form of brain signals, brain electrical signals, measured from EEG caps. And we see that differentiating or categorizing animals versus animals is a very complex task. Yet humans are capable of doing that at 150 millisecond after the onset of the stimuli. And this is remarkable speed given the wetware we have between under our skulls. Also, neurophysiologists have taught us that objects is a very important functionality in our visual intelligence in humans. So important that there are neural correlates in our brain, areas that are dedicated to object understanding, such as face areas or place areas or body parts areas. This shows that evolution has really spent time to hone in our visual intelligence skills when it comes to object recognition. So all this built up the history for the field of computer vision that a few decades ago, object recognition became a fundamental building block for visual intelligence, and we want to empower machines with that. And in order to do that, we define the problem, or at least the original problem, as given an image, how do we enable a computer to call out the objects or what the object is in the image? That's such an effortless task for humans. But if you think about it, now that you've learned enough computer vision to know that mathematically there's infinite possibilities to actually recognize any object because of different lighting, texture, background, occlusion, viewing angle, scaling, and whatever, you name it. So this is actually fundamentally a difficult task. The history pre-deep learning is also very interesting. There were some pretty heroic attempts at solving the problem of generic, generalizable object recognition. And the first wave of attempt was actually very inspired by psychology itself. We self-introspect sometimes even to the detriment of over self-introspection. We think that humans compose parts, right? Like we look at objects, we can see geometric parts, and then we can compose them into different objects. And that idea of using pre-designated parts or shapes and to, compose them in specific ways was the first wave of object recognition. So these are different work or models coming from the 70s, 80s, or even going all the way to 90s of using different parts and configurations to recognize objects. Of course, it didn't really work. It's mathematically beautiful and simple, but it didn't work. So a second wave of object recognition pre-deep learning was actually a really important era in the field of AI. Is really the beginning of machine learning, statistical machine learning. It was the marriage between computer programming and statistical modeling. And with that marriage, we start to realize the world is so complex. These problems, these intelligence problems, whether it's visual intelligence or language intelligence or other kind of intelligence, in order to generalize, we need to learn learn the parameters. It's very hard to use hand-tuned models to get good learning. We now know we need data, even though we didn't at that time know how much data, but we also know that we need to design or architect statistical models so that they have the capability of learning through different learning rules. And because of that, we saw a blossoming of models in that era where we're learning, random fields or Bayes nets or support vector machines and all that. And in fact, a lot of progress was made by the time we are in the first decade of 21st century in object recognition, that we even have international benchmarks of a small number of object classes to encourage everybody to compare their algorithms. So we're inching together. The last unlock for object recognition, as we have learned, again goes back to cognitive science. So this particular psychologist, Irv Biederman, had long conjectured that humans can recognize a huge number of objects. And this is intuitive for our common knowledge, but he actually put a number on it. I personally call it the Biederman number, which is that by, age 6 or 7, children, he conjectured, were able to recognize about 30,000 to 100,000 different visual categories. And he used this, where did he come up with this number? It's a combination of looking at dictionary, the number of nouns, as well as visual studies of how kids recognize different objects. But it's a number that's pretty daunting and pretty sobering for the field of computer vision, because up till now, this is middle of the first decade of 21st century, we were working with tiny number of object categories and a tiny number of images to work with compared to what humans experience. And this was, as you know, the onset of the motivation for ImageNet project, which took this Biederman number really seriously and we constructed this data set that is on par with what the psychologist Irv Biederman conjectured, which is around 22,000 object classes over 15 million images. And of course, that's the beginning that you start to come into this class, is that because of the large data provided by ImageNet, we start to see that powerful algorithms like neural network, at the beginning it was convolutional neural network, of course now we use transformers and all that, start to really show their power through big data. And this is a generic slide for those people who didn't learn about this. I'm going to skip this because you all know this. So the quick history is, as soon as we have ImageNet, as soon as we use convolutional neural network a few years after the beginning of ImageNet, we saw this door blasted open in terms of solving the problem of object recognition. Now we have algorithms that we can take to look at any picture in the world and be able to recognize objects in the big or small and in any kind of, orientation. It's not, is it 100% solved? No, there's always long tail problems we can solve. But as far as industrial application goes, this has come a long way and really has been a matured problem. And of course, all of you know, and all this came at the convergence point, which is the year 2012, where the ImageNet Challenge provided the data for the convolutional neural network, and they used 2 GPUs at that time, and the 3 ingredients come together and brought the moment of deep learning, the birth of deep learning. And in this class, we also talked a little bit about different various architectures that ImageNet Challenge engendered throughout the past decade or so, in terms of, convolutional neural network or ResNet and so on. So that's the beginning really about deep learning revolution. And of course, in terms of the quest for visual intelligence, we're not going to stop at just being able to label objects in a scene. For example, in these two scenes, right? If you just label objects, you'll think it's just a llama and a person. But if I show you the second scene with the llama and the person, the story is completely different. Even though you have the same object, you have very different relationship. So cognitive scientist, once again, was a head of computer scientists, and inspired us to think about visual intelligence beyond just naming objects or categorizing objects. In this particular paper, Jeremy Wolf, who is a pretty prominent psychologist, wrote this beautiful paper that called out that relationships between objects must be coded as part of our understanding of complex natural things. And inspired by that work, the field of computer vision start to look at how do we understand relationships. And this is early work. You guys got a lecture from Ranjay, and last week, last week, this was his PhD thesis, looking at learning object relationships using scene graph as a representation. In this case, scene graph is defined by these entity nodes that are objects, and their relationships are defined by the connectivity between the nodes, or sometimes they have attribute relationships that defines the particular objects. And even a scene as simple as this, with mostly just two people, one feeding a cake to the other, you can form a very dense scene graph because of the richness of the visual scene. And this was Ranjay's thesis after the image net object recognition era, where we build a data set called visual genome, where we try to put together object relationships, also story descriptions. And one of the work that Ranjay did, I thought that was really fun, was zero-shot learning of unusual object relationships. For example, it's not unusual to see person riding a horse. It's not unusual to see person wearing a hat. But it's unusual in general to see horse wearing hat. And in the era of big data training, it's hard to get this kind of data repeatedly because you just don't have too many of that. But using this compositional scene graph representation, we're able to learn the more common relationships and then derive uncommon relationships in that representation. And again, this is another example of zero-shot learning where, person sitting on chair and fire hydrant on the lawn or on the field are all common relationships, but person sitting on fire hydrant is the one that would not. It's hard to get data, and we're able to do that, to make that happen. And this is just a figure from the paper that shows that Ranjay's work at that time achieved state-of-the-art recognition rate compared to many other methods. But relationship is not enough, right? The ability to actually tell a story that is a lot more richer, or also using natural language, is actually the next big goal. So around the year 2014, we start working on that problem. And think about it, that's just 2 years after the ImageNet AlexNet moment. But the field was starting to evolve so fast. We're so inspired by what we can do using a combination of convolutional neural network as well as a language model called LSTM. And this is the thesis by Andrej Karpathy, that we were one of the first teams that showed how to do image captioning or storytelling, as well as dense captioning which is also part of the work that Justin Johnson did. And I know he's one of the co-instructors of this course. And that was around the time between 2015 to 2018, a lot of work has happened to solve the problem. Of course, today, using multimodal LLMs, we have taken the solution of this problem even to another notch. But this is the beginning of that line of work. And frankly, I myself, as a computer vision scientist who entered the field at the beginning of the century, was very surprised by how fast our field was able to solve this problem as soon as we've got data as well as neural network algorithms. But a much harder problem is actually in dynamic scenes. In dynamic scenes, we tend to have much more complex relationships, much more complex movements, and the camera, also the camera movement or the entity, the actors within the scene can do a lot of different things. So in this work, that a collaboration with Isan and a bunch of students in our lab, we call it multi-object, multi-actor activity understanding. This is a much newer work. We only published this a couple of years ago to capture the relationship between these actors and their activities in dynamic scene is still, I would say, an unsolved problem. And this will have profound implication. You know that you're in Silicon Valley, so you're hearing so much excitement of robots, for example. If we ever dream to have everyday robots that work amongst us, robots need to solve this problem, understand how complex the scene is, what people are doing, who is doing what is next, and this is an unsolved problem. Also, you know, in addition to what I have shown you, you have learned a little bit in this class and related computer vision problem, but we didn't have time to elaborate. For example, 3D computer vision or human pose understanding, and of course, generative AI and generative models. So this is just to show you that the field of computer vision since the rebirth of modern AI has been just moving extraordinarily fast. But the take-home message in this section for me is that two things. One is that data compute and neural network algorithm truly have converged about 10 years ago or 13 years ago. And that was the moment that modern AI or deep learning revolution has happened. But the history of that and so much of the problem that we have been working on is truly inspired by cognitive science and psychology and neuroscience. And that to me is is going to continue to happen, is that we will continue to be inspired by what the brain can do or how the brain does things. And also we'll continue to use AI to help our brain research. So there is a very intimate relationship between today's AI and cognitive science, neuroscience, brain science, and all that. So that's the first section. And of course, a lot of people, students and collaborators have contributed to what I have just presented. Now let's talk about going beyond just building AI to see what humans don't see. This is where pushing AI beyond the capability of humans, or you can call it superhumans. For example, most people don't recognize a ton of dinosaurs. You can probably name a few. Some kids really can name a lot. Well, let alone thousands and tens of thousands of bird species, or tens of thousands of car categories. So this is the line of work that I call fine-grained object categorization. Humans are just not that good at it. And this is still a problem that I don't think we're fully solved yet, to be honest. In this generative AI era, especially we're talking a lot about multimodal LLMs, this problem has somewhat been neglected, or it just is not a mainstream problem. But it really will, still will come and play an important role. So in this early work of fine-grained bird species recognition, we put together, a data set. Actually, we used a data set of 4,000 birds. And as you can see, as we go down the tree of the species, the eras, actually, as we go up the species, as we have generalizable, more general names, the error decreases, but which means it's a convoluted way of saying by the time you're in the fine-grained level, we still make a lot of errors. The algorithm are still not totally ready. Another work that I find fascinating is that a few years ago, a group of students and in my lab trained a fine-grained car classifier in terms of make, model, and year. It turns out after 1970s, there are thousands of car models that are defined by different make, model, and year. And then you can we took Google Street View images from 200 or 100, I think, major cities across the country. And then we use the fine-grained car detectors to detect what are the cars on the street of these cities. And we use it as a lens to study social patterns. For example, what is the pattern here I showed? Education patterns. Car models and education patterns are highly correlated. Or income patterns, highly correlated. In that paper, we show voting patterns, highly correlated. Or even environmental, patterns, highly correlated. So it's a really interesting way of using computer vision as a lens to study our society. And no individual human, not even a collection of humans can do this easily at all. So AI is really pushing the boundary of what humans can see. To drive home this idea, let's do a couple of tests. Humans have our limitations, right? I just talked about celebrating humans' ability of seeing, but we also have our limitations. This is a very famous visual illusion test called Stroop test. And the idea is that you all can read the words, but if I ask you to read the color of the word as fast as possible, going from left to right and top to down, you find it's not that easy, right? Try to read it like red, yellow, green, purple, blue, black, orange. It's fighting with you. This is the fight between visual attention and all that. Here's another example. There are two alternating images of the picture, and there's one change, a pretty big change that's happening between the two alternating pictures. I don't know if you spot the change. Do you spot it?
The engine.
Yes, it's the engine, right? So it takes a while to spot it. So this is a very famous psychology experiment called change blindness. Now, all this is fun. Stroop test is fun. This is fun. But this is not fun. That human attention is limited. And in some situations in our work and life, that kind of attention limit can be dire. For example, medical errors are the third leading cause of death in America's healthcare system. And of course, leaving a pair of scissors in the body of the patient is kind of the iconic image of medical errors. But there are so many medical errors, pharmaceutical errors, there's, procedure errors, clerical errors, diagnostic errors. So one has to be very careful. For example, in surgery rooms, Honestly, scissors don't get left in the bodies typically, but much smaller things like suture needles or a piece of gauze and all that. So today, most of this is still just tracked by hands, right? Like we have these checklists to track in the surgery rooms. If something is missing, the surgery has to be paused. On average, that pause is close to an hour. And think about the danger for the patient, the exposure to bacteria and the bleeding and all that, just because we have to search for that item. So if there is a way to use AI to help our doctors, surgeons to track items, that would be so powerful. And this is just a demo. This is not a deploy system. We're not there in terms of fidelity, but this is a demo to show that we can use AI to count, in this case, gauze, and all that. And this is just an example of pushing AI to see what humans don't see. Here's another example that is really fun. I don't know if I showed this before, but this is one of my favorite visual illusions where I'm just giving you the answer. If you look at the two square A and B on a checkerboard on the top, it is so hard to believe they have the same grayscale or luminance. And then you look at the bottom, you're like, of course they do. But why? Even though you have the bottom picture in front of you, seeing the top, it still gives you the illusion. Why? Because evolution has pre-wired us in conjecturing or understanding our world in its common way, with the common physics of the shape of objects, lighting source, how shadows are made, and all that. This is so deep in our evolution, in our visual development, that it's hard for us to see it another way. So what I'm trying to get at is there's bias in our human visual system. The bias might come from evolutionary construct. The bias can come from our social experience. The bias can come from the data we're exposed to. But some of these biases can be harmful, right? When the bias happens that became unfair to a group of people, a community. And we have to be aware of this. A few years ago, face recognition algorithm was not good, and it tends to recognize certain skin color and even gender better than the others. And it has consequences. Think about self-driving car. So think about, many other medical use cases. So we have to be vigilant about this. I do believe that AI bias has been a problem that people now are carrying. A few years ago, this problem was so new that many people are not even paying attention. But fast forward to 2025, I'm not saying we have solved this problem, but I'm personally a lot happier to see that so many people are paying attention to this, not only just in academia, but also in industry. And then there's another kind of not seeing. And this is interesting. Sometimes not seeing is exactly what we want, because you want to respect privacy. So how do you create AI that helps people to see, yet you still want it not to see what people don't want you to see? This is a very deep, it's a technical problem as well as a human problem. So from a technical point of view, there are many ways to consider ML, machine learning privacy. I'm just listing here from a visual approach point of view. A few years ago, our lab wrote this paper about using smart cameras in patient rooms or patient homes to help doctors to see better. But even there, we have to recognize issues like faces or just full body information, and even homes. And this is a list of potential solutions. For example, you can do blurring, or you can do masking, you can do dimensionality reduction, but you can also, try to do different approaches, for example, federated learning, so that you don't send all the data to the server, or encryption and other things. So I'm not going to belabor this, but there's one work I want to show you. It's not even my work, but I really like this work. And it's a work about taking videos of people and try to recognize the action of people, but yet respecting the privacy of people. How do you do that, right? For example, in this case, you want to take a video of this kid moving in a scene. There are ways to do this. If you blur this, or defocus this, or do some of these, it kind of, you can provide, you can protect privacy, but you also lose enough information that you might not even know what this person is doing. And for many applications, the whole goal is to know what this person is doing. So in this particular work, led by Juan Carlos and students, they actually did a combination of hardware and software approach, where they had crafted a lens that is actually that actually filters visual data in a particular way. So particular that if you look at the top row, the lens, what the lens captures into the camera protects the privacy a lot. You don't see the person's face, you don't see the body, and so on. But because it's a lens that's particularly designed in connection with a piece of software, it can help to back out the movement information or the human activity information without backing out face information. So that's a really interesting approach. That's a hybrid between hardware and software, aiming towards important applications that you want to see people to protect them, but you don't want to see too much because you want to respect privacy. So that's a work I really like. I really like the spirit of that work. So, okay, so in this part of the lecture, I shared with you a number of things, just considerations of building AI to see what humans don't see. Sometimes we're pushing AI, like fine-grained recognition of birds, to go beyond human ability. Those are superhuman ability. Sometimes we know humans are not good. We have bias, or we have attention issues, and then we want to use AI to help us. And then sometimes we generally have situations we don't want anyone to see. And then how do you use AI to continue to help without violating those privacy concerns? So you can see that AI is a very interesting, powerful tool. It can both help but amplify us. And if we have bias, if we have issues, AI can amplify us too. So when we build AI, it is so important not only to take that technology perspective, but also to take the human perspective, to commit to study, forecast, and guide the AI to understand its human impact and respect human values. So that's the second message, take-home message. And again, a number of collaborators and students participated in this work. Okay. Now let's talk about building AI to see what humans want to see. And in fact, we're going to go beyond seeing. We're going to connect seeing and doing together. So if you think about today's societal anxiety about AI, one of the biggest anxiety is labor. A lot of headline news will say labor is under threat, robots taking over jobs. The truth is the picture is complex. Denying job change is wrong. Every technological shift in human history has caused labor market change. And some of them are very painful. Some of them can lead to even civil wars and wars. But also that change sometimes is inevitable. And a tiny digression. A lot of the labor threat rhetoric that we have been hearing, think about physical labors, But today, in the past 2 years, if you look at Gen AI's impact, is white-collar jobs that are drastically being impacted, especially software engineering and analytical work in offices. So there's just definitely labor change. But in the meantime, we also need to recognize that AI also can be helpful. We actually fundamentally have human labor shortages in many situations, especially in elderly care as well as healthcare. First of all, as modern medicine improves, human life expectancy increases. And that just inevitably pushes a society towards longer living. And that's a good thing. But in the meantime, we have shortages of laborers. Young people need to work. And that's how to make this society vibrant, economy vibrant. But who is taking care of our elderlies? Who are taking care of our chronically ill? Even in America's hospital, we have such an attrition of healthcare workers, especially nurses, that we don't have enough hands, ears, eyes to help our patients. So instead of thinking about this word replace, we actually can think about AI augmenting. And you got a glimpse of that in my surgery room example. Indeed, in healthcare, there's so many spaces in healthcare that we don't have enough pairs of eyes. And that's what I call the dark spaces of healthcare, from surgery room to patient room to pharmaceutical to homes and so on. So how do we make AI help? And this is something that Isang has been leading a ton of this work, also with Zing, is that we have been looking at this problem of ambient intelligence for healthcare, where we combine smart sensors with machine learning algorithms to glean health critical insights from these situations in healthcare setup, so that we can alert the patients or family members or doctors in time to help patients. And again, the fuller paper is in this particular paper we published a couple of years ago. Let me just give you a couple of examples. One example is this hand hygiene project, which actually started way before COVID. Hand hygiene turns out to be really important for keeping hospital infection low. Hospital-acquired infection is actually one of the leading causes of American patients' fatality in our hospitals. It kills more than 3 times more people per year than car accidents nationwide. And it is really hard to control. Most of these germs are passed from patient room to patient room, and then they kind of just brew together. So what do? The hospitals try to use human auditors, but we just talked about, we don't even have enough nurses, let alone hiring auditors. And also you cannot hire enough of them. There's human fatigue. We just talked about human attention problem. So this is not a pretty prohibitive solution. There were some technological solutions like RFID, put the badge, if the badge or the person wearing the badge is close to the sink or the hand hygiene, hand sanitizer dispenser, it gives you the hint that the person, or most likely the doctor or the nurses, is washing their hands. But that's very non-specific. You cannot guarantee. And the hospital rooms are pretty small. Corridors are small. And just standing next to something doesn't mean you're doing it. So a few years ago, we did this project where we put smart sensors that protects privacy by just only gleaning depth information, like the blue screen, the blue video there. And then we use computer vision algorithm to classify actions. Is the person washing hand or not washing hand? And the result is that if you compare ground truth with the algorithm output versus human outputs, or human detection results, you can see algorithm is so much better and more consistent than humans. You have to almost show the same video to 4 humans to get almost as good as AI. And this is just not plausible. If it's one person, you can see how sparse the detection is, and that's not good. So this is one application. Another application we worked on is ICUs. ICU is where patients fight life and death. ICU is also where 1% of US GDP is spent. So making ICU as effective, as safely as possible is a top priority. One of the the goal of ICU is to get our patient safely out of ICU and go into step-down units or even go home. So one of the most important thing people have learned in ICU is to help patients to move. Proper movement, which we call mobilization, is actually important for recovery. But this is a very dicey situation. You have to get nurses to help, doctors have to give orders, and you have to move properly, and it has to be in different time, like designated time, and you have to assess the movement. And all this is not easy, right? So we collaborated with Stanford as well as Utah's Intermountain Hospital to put these smart sensors in ICU units and help doctors to monitor patient movement. In this particular case, 4 different kind of movements: getting out of bed, getting in bed, getting out of chair, getting in chair. These things are so important for ICU patients. I know that for us, it's a no-brainer, but this really is critical. And you can see that AI can help to do the kind of detection and prediction that is so helpful for doctors, especially when there's a labor shortage. Last but not the least example is aging in place. And this is just so important for, many reasons. Seniors want to live home independently and healthily. And remember during the beginning of COVID, when we had so much fatality among the aging seniors, a lot has to do with hospital overrun and overtaxed hospital system. So keeping seniors safe and well in their homes is really critical. And using smart sensors, we can help, early detection of infection, especially using thermal cameras. Or mobility, we just talked about in ICU, similar here, or understanding sleep patterns, or understanding dietary patterns. All this are realms of possibilities by AI and smart sensors. And then last but not least, what if there's still labor shortage after smart sensors? The thing about smart sensors is that they're information gathering system, but they cannot go there and help to turn a patient or bring water and medicine pills to the elderly. So this brings us to the last technical topic, which is embodied AI, or we would call a large part of embodied AI is robotics. And this is where I find it extremely exciting because it closes the loop between perception and action. And if you think about the Cambrian explosion of evolution, when there's an onset of eyes, animals start to move. So the area of robotics is where we can close the loop between seeing and doing. But it's not easy, right? Robots, as much as we're very excited by them, still are very, very slow. They are very, very clumsy. It's very hard for them to adapt to a generalizable situation. And in today's robotic research, we as a field have made a ton of progress, and Stanford is definitely one of the centers of robotic learning. But still, most of these work are kind of constrained in their setup, are short horizon tasks like pick and place, and it has anecdotal setup and lack of standard benchmark. So let me just share with you a couple of work in our lab. One work is a few years ago, we're looking at how to bring robots to the wild. If we have to pre-designate the set of tasks, it's kind of unsatisfying. On the other hand, if you look at today's LLM, it's totally in the wild. You can talk about anything. So my student Wenlong and a few students want to close this gap. So this idea is that how do we give an open instruction to a robot, any instruction, without pre-training everything in a closed world, and the robot can do some tasks. So let's say your training set is open a door like that. In the wild, you have doors like that. So how do you make some progress in that problem? And so the goal is in the wild generalization. And here's a result, or overall algorithm. I don't know if this is so glitchy, but whatever. What you're saying is we want to tell this robot arm to open a drawer by planning a motion path that avoids knocking down that flower. And all these instructions were not pre-trained. So what we do is actually we borrow the latest advances in LLM as well as in visual language model. And the idea is that we use LLM and LLM to give us an instruction set. And then we use visual language model to help us to recognize or understand the environment. And then we turn that into a motion planning map so that the robotic arm can execute. And because we're using LLMs as well as VLMs, we don't have to, we get rid of the problem of training robot in a closed world and bring them to a more generalizable or in the wild. And the details is the instruction of open top drawer comes in. LLM turns this into like literally codes. And then because of these instructions like drawer or handle, we send this information to a VLM model, and that model detects drawer and handle in the scene. And then because of that, it updates its information, and then it updates a motion map. This is presented by a heat map to show you where the robot arm should focus, where it should not focus. And with that, then you give it another instruction, but watch out for the vase. Again, it goes through the same thing with LLM, writes the code or generates the code, send it through a VLM model. VLM model detects the object and then updates the motion planning map. In this case, it's the negative, not the positive, because you want to avoid that. And then combining with the previous map, you get a heat map of knowing where to avoid and where to go. And eventually, what we do is we do this for the motion planning map, we do it for rotation, to gripper, velocity, and then this is the result. Actually, let me just show you this. This is the actual result of the robot. And then we do this for many different tasks, right? We can do it for articulated object manipulation. We can do it, we can, here just many different examples, napkins or sweeping the floor. What is this? Getting toast, setting up table, and also dealing with online disturbances and so on. So this is one work. Another work I want to just show you quickly is that overall robotics research is still lacking good benchmark, and while we're still experimenting in the labs, we know real world is so much more complex, so much more uncertain, have large variability, is so interactive and social, and has a lot of multitasking tasks. And then we know that both natural language and computer vision has benefited a lot from setting up important large-scale data sets for both training and benchmark. So in our lab, we have been working on this project that is towards an ecological robotic learning, building an ecological robotic learning environment, and try to encourage researchers to benchmark against a large and diverse set of activities. And that's the behavior benchmark, which is benchmark for everyday household activity in virtual, interactive, and ecological environments. Now, here's a question, because this lecture has a lot to do with human values, is who is to say which tasks robots should do? I know that every graduate students who are working on robotics just want two tasks. One is laundry, the other one is dishwasher. That's great. But moving beyond grad school, what are the tasks we should get robots to do for us? So instead of us coming up with this task list, we actually did a human-centered survey to ask to ask humans that what would you like robots to help you? Let me test this. Would you like a robot to help you to clean the kitchen floor? Say yes or no. Okay, good. Normal people would say yes. Shoveling snow. Okay. Folding laundry. Okay, good. Cooking breakfast. See, we're getting mixture answers, right? What about opening Christmas gift? Right, exactly. People are different. Like, I actually think robot can do this pretty well, but we don't want it. We even ask, one of the tasks we ask is buying wedding rings. Can you imagine that? So what we did is actually, we want to respect human preference. So we took a bunch of government surveys from labor office in US and Europe and so on, and put together thousands of everyday activity tasks. And then we went online to find people. We want to be as diverse as possible, but I think we have room to improve. But we found 1,400 people and to answer these tasks and tell us which tasks they want robots to help. And then we rank that. And you can see that just like grad students, people want robots to help with cleaning, a lot of cleaning, toilet cleaning, floor cleaning. But people don't want robots to play squash for you, or to buy a wedding ring, or to even mix baby cereals. There's a lot of tasks that matters to us as humans, emotionally or socially or whatever. So our goal is first, we decided, we have a principled way to decide which are the 1,000 tasks that we want to train robots for. And those are the tasks that humans prefer to get help. And with that in mind, we have to actually build a virtual environments. So we scanned or acquired 3D scene from 50 different real world environments, from restaurants to apartments to grocery stores to offices and so on. And then we acquired, this number is actually outdated. We acquired more than 10,000 object assets, 3D assets that has a lot of properties, whether it's articulation, deformability, and all those properties. And then we have to build a simulation environment. A lot of people have built simulation environment. Let me just fast forward. But our particular simulation environment was a collaboration with NVIDIA's Omniverse group. And we were going for building a physically, perceptually, and also interactively high quality simulation environment. And this, especially taking account, for example, physical effects like thermal transparency, deformability, and so on. We also tested our behavior environment against other environments in terms of perceptual realism from human user study. And, here are some of the examples of physical interaction, such as cloth or liquids and so on. So there's a lot of nuance that has gone into this work. And let me just fast forward. And these are some benchmark we did compared to other work. Okay, let me just fast forward. So this is ongoing work actually in our lab. And because of this, we're able to, we are using behavior to help us to learn robotics, to help us actually to push us to gather more interesting data, and also to use that for even cognitive studies. Let me just fast forward. One thing I want to share with you is that, let me just share these numbers, is today's algorithms still cannot do behavior tasks. And of all these roles, the top role is what we wish robots can do. Give them no privileged information. They have to be dropped in the environment and do these tasks. And we benchmarked 3 behavior tasks using today's robotic algorithm. And the performance is just 0. Once you start to give more privileged information or make assumptions that make the task simpler, like magic motion or some, perfect memory and all that, things start to get better. So this is if you look at it, only look at the top row, you get pretty depressed by today's robots. But as a grad student, I hope you're inspired, because that means we have a lot of room to grow. Okay. These are just different papers from our lab. I'm going to actually fast forward because I think we've talked enough about this. By the way, we're also doing digital twin of behavior in the digital environment as well as in the real world environment, and that's a great way of testing real to sim transfer. Again, this is an unsolved problem. And there's a long way to go. And in this particular case, we're showing you that this robot, without speeding up, you can see how slow it is trying to clean up this room. And, okay, hooray. This is actually, some of the mistakes that this robot, makes for example, it cannot pick up the bottle, or earlier it just went the wrong way and placed it in the wrong place. So there's still a lot of mistakes. Okay, let me fast forward. We're also using this environment to study visually impaired patients, and this is a great way of putting patients in a safe environment to study. One last thing I want to show you is really super cool, and this is the last technical work I want to show, is that we also now are collaborating with psychologists and doctors to study how we can use brain waves to control robots. So what you're seeing here is a demo where a grad student, I think, is wearing this EEG cap, and that just is sending instructions. And the robotic arm is cooking a Japanese meal purely from thoughts. There's no invasive brain control. This is from electrical signals. What we had to do is to pre-train these thoughts. You have to pre-train the robotic arm with, say, lift or place or drop or whatever. And once you do that, this is an entire meal cooked based on the wave. This is really sci-fi, and this has happened last year. So I'm pretty excited by where all this is going, combining vision and perception and robotics, and also, helping people in clinical setting. This is really, the future of this is helping severely paralyzed patients. Okay, so behavior project is really aimed at augmenting people. It's a large scale, diverse benchmark, and it has realistic and ecological, physics and perception. And this is the last part of what the last take-home message is, that we not only want to build AI to just do things or see things, we really want to build it to help people. AI being an augmentation tool or enhancing tool for humanity is very important instead of a tool that replaces us.